Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about giant moment generating function. Giant moment generating function. In my previous videos, second unit, we have already discussed about moment generating function concept in single random variables. Now here giant random variables. Giant random variables mean two random variables or more than two random variables. Giant moment generating function concept. Let x1 and x2 be two random variables with giant probability density function is fx1 x2 of x1 comma x2, or this density function is also denoted as f of x1 comma x2. Then their giant moment generating function is defined as m suffix x1 comma x2, m suffix x1 comma x2 of t1 comma t2 is equal expectation of e power x1 t1 plus x2 t2. So this is the two random variables giant moment generating function definition. In single random variables, x1 is the random variable. The moment generating function of the single random variable definition is m suffix x1 of t1 is equal expectation of e power t1 x1. So now we are the two random variables. This is the giant moment generating function definition. If capital X1 and X2 are discrete random variables, then the giant moment generating function is given by defined as m x1 x2 of t1 comma t2 is equal sigma I is equal to 1 to n, sigma j is equal to 1 to n e power x1i t1 plus x2j t2 into probability of x1i comma x2j. For the discrete case, this is the definition of the giant moment generating function. For continuous case, if the random variables x1 and x2 are the continuous random variables, then the giant moment generating function is given by m suffix x1 x2 of t1 comma t2 is equal integral minus infinity to infinity integral minus infinity to infinity e power x1 t1 plus x2 t2 into giant probability density function into dx1 dx2. So now here T1 and T2 are not a type. T1 and T2 are the variables. So this is the definition of the giant moment generating function, and this is the definition of the giant moment generating function for discrete random variables, and this is the definition of giant moment generating function for continuous random variable. And next we are going to discuss about properties of giant moment generating function. And the first property is the marginal moment generating function can be determined from the giant moment generating function. So that is m suffix x1 of t1 is equal to m suffix x1 x2 of t1 comma t2, and m suffix x2 of t2 is equal m suffix x1 x2 of 0 comma t2, and also m suffix x1 x2 of 0 comma 0 is equal to 1. So this is the property of marginal moment generating function of the random variable from the giant moment generating function. So mx1 of t1 is the marginal moment generating function of random variable x1. mx2 of t2 is the marginal moment generating function of random variable x2. And next, coming to the proof, consider two random variables, capital X1 and capital X2 are the two random variables. Then the giant moment generating function of two random variables is given by m suffix x1 m suffix x1 x2 of t1 comma t2 is equal expectation of e power x1 t1 plus x2 t2. In this equation, first substitute t1 is equal to 0, we get marginal moment generating function of random variable x2, and let's substitute t2 is equal to 0, we get marginal moment generating function of random variable x1, and let's substitute t1 is equal to 0 and t2 is equal to 0, we get this one. If t1 is equal to 0, then mx1 x2 of 0 comma t2. So in this equation substitute t1 is equal to 0, we get expectation of e power x2 t2. So that is expectation of x2 t2 is the single random variable moment generating function definition, which is m suffix x2 of t2. If t2 is equal to 0 in this expression, in this definition, substitute t2 is equal to 0, m suffix x1 x2 of t1 comma 0 is equal expectation of e power x1 t1 is equal to so expectation of e power x1 t1 is the single random variable moment generating function definition. Sorry, expectation of e power x1 t1 is the single random variable moment generating function definition. So that is m suffix x1 of t1. Next substitute in this expression t1 is equal to 0, t2 is equal to 0. Then we get m x1 x2 of 0 comma 0 is equal to expectation of e power 0. E power 0 is 1, expectation of 1 is 1. So this is the first property of the joint moment generating function. The second property is if two random variables x1 and x2 are the independent random variables, then m x1 x2 of t1 comma t2 is equal to m x1 t1 into m x2 t2. If the random variables x1 and x2 are the independent, the joint moment generating function is equal to product of their marginal moment generating functions. That is this one. So now coming to the proof. X1 and x2 are the two random variables with their giant probability density function is f of x1 comma x2. Since x1 and x2 are the two independent random variables, we know that the condition of the probability density function of the two independent random variables f of x1 comma x2 is equal f of x1 into f of x2. So we know that for the continuous case, the joint moment generating function expression is m x1 x2 of t1 comma t2 is equal integral minus infinity to infinity integral minus infinity to infinity e power x1 t1 plus x2 t2 into joint probability density function into dx1 dx2. So now here the random variables x1 and x2 are the independent random variable. So the condition of the giant probability density function is equal to product of their individual density function. That is f x1 x2 of x1 comma x2 is equal to f x1 of x1 into f x2 of x2. And this exponential term is arranged as e power x1 t1 plus x2 t2 is arranged as e power x1 t1 into e power x2 t2. So on RHS side of all these terms are the product term. So RHS term is also written as integral minus infinity to infinity e power x1 t1 into fx1 of x1 dx1 integral minus infinity to infinity e power x2 t2 into fx2 of x2 dx2. So using the definition of marginal density function of the marginal moment generating function definition of for the single random variable case, the first integral term is marginal moment generating function of the random variable x1 and the second integral term is marginal moment generating function of random variable x2. So that is m x1 of t1 into m x2 of t2. So this is the second property proof. Next third property is if two random variables x1 and x2 are the independent, then m x1 plus x2 of t is equal m x1 of t into m x2 of t. If the random variables x1 and x2 are the independent, then m x1 m suffix x1 plus x2 of t is equal to product of their individual moment generating function. That is this statement. So now coming to the proof, random variables x1 and x2 are the two random variables with their giant probability density function is f x1 comma x2 is equal uh, with their giant moment generate with their giant probability density function is fx1 fx1 x2 of x1 comma x2 are simply denoted as f of x1 comma x2. If x1 and x2 are the independent random variables, we know that giant probability density function is equal to product of their individual density function, that is f of x1 comma x2 is equal to f of x1 into f of x2. So for continuous case, the joint moment generating function definition is now here we want to prove that mx1 plus x2 of t. Okay, so m suffix x1 plus x2 of t is equal to, for continuous case, integral minus infinity to infinity, integral minus infinity to infinity e power x1 plus x2 of t into giant probability density function into dx1 dx2. So this x1 x2 are the independent random variables. This giant probability density function is equal to product of their individual density functions. This e power x1 plus x2 into t is written as e power x1 t into e power x2 t, and the RHS term is also written as, all are the product term. So the this RHS term is can be arranged as integral minus infinity to infinity e power x1 t into fx1 of x1 dx1 integral minus infinity to infinity e power x2 fx2 of x2 dx2. So using definition of moment generating function of the single random variables, the first term is marginal moment generating function of x1, and the second integral term is marginal moment generating function of x2. So that is mx1 of t, second integral term is mx2 of t. So these are the some important properties of joint moment generating function.